Hey, welcome back. Today we'll be discussing about computing the input impedance across a pair of nodes through the example of a current mirror. In analog IC design, we often talk about the input impedance looking into a node, but seldom do we talk about the input impedance across a pair of nodes, which might be useful in some cases. For instance, the input impedance across a cross-coupled pair finds useful applications as it turns out to be minus 2 over GM. A quick disclaimer that this concept is borrowed from Dr. Ali's article published in the Solid State Circuits magazine. Let's dive right into the topic of today's video. The procedure is rather simple. We inject a current Ix in one node and pull out an equal and opposite current from the other node. Next, we compute the generated voltage Vx across the two nodes. Let's begin with the small signal model. We have a current Ix flowing into the impedance of R0 in parallel with 1 by Gm. This yields a voltage of V1. So V1 will be equal to Ix over 1 Gm plus 1 by R0. Simplifying this, we get V1 equals to Ix multiplied by R0 upon Gm R0 plus 1. Now we have a current Ix flowing and we have GMV1. The cumulative current flows into the output impedance of R0. Thus, the current flowing through R0 is the sum of the two I, which is Ix plus GMV1. So the node voltage V2 will be minus I times R0. And we can write I as Ix plus GMV1. Therefore, minus V2 equals to Ix plus GMV1 times R0. Simplifying this equation and plugging in V1 from the above calculation, we get the following term. Now let's calculate the difference of the two voltages V1 and V2. So Vx will turn out to be Ix R0 by Gm R0 plus 1 plus Ix R0 plus Gm Ix R0 square upon 1 plus Gm R0. We can recognize that the first and the third term can be added to yield Ix R0. So 1 plus Gm R0 cancels in both of them, and thus we are left with Ix R0 plus Ix R0, which is 2 Ix R0. So we wish to calculate the ratio Vx by Ix, which is the input impedance, which turns out to be 2 R0. That's surprising. Next, let's also look at the ratio of V2 by V1. So if we neglect 1 in front of Gm R0, we get V2 equals to Ix R0 plus the Gm R0 term cancels off. So we have another Ix R0, and thus V2 is approximately 2 Ix times R0. Similarly, if we can neglect 1 in front of Gm R0, in the expression for V1, we are left with Ix R0 over Gm R0. The R0 cancels, and thus we have Ix over Gm. So the ratio of V2 by V1 comes out to be 2 times Gm R0. This is unique in the sense that in a purely differential operation, we expect V2 and V1 to be the negative of each other. However, here we see that the magnitude of V2 is much larger than the magnitude of V1. Alright, that's it for today, folks. Thanks. Until next time, peace.